Thank you for taking the time to view this presentation. Continuous insulation requirements have been in the International Energy Code since 2009. The 2015 version of the code included a definition of continuous insulation, as many people in the industry were using their own interpretation of the term. The intent of the continuous insulation requirement was to minimize thermal bridging through the insulation, as thermal bridges reduce the effectiveness of the insulation. The definition made the use of continuous Z-furring for the attachment of cladding systems a violation of the code. Several companies have developed products and assemblies to comply with the code requirements. We looked at them and we didn't like any of them, as they all had shortfalls, some more than others. So we invented our own, the Stand Off MPV Bracket. The first thing we did was make a list of all the requirements for a cladding attachment system that we thought were necessary. And these were: they had to withstand the loads imposed upon it, of course. They had to comply with IBC and IECC requirements. We didn't want ours to burn so that they could be used in non-combustible construction types. We wanted to result in minimal thermal bridging through the continuous insulation. We wanted to install easily with few parts to assemble. We wanted to provide the required adjustability within the bracket so as not to need shims to install the cladding system. We wanted the cost to be reasonable. We didn't want it to require cutting and fitting of the continuous insulation around the brackets, as this creates more labor. And what was very important to us was we wanted it to provide the mechanical fastening of the continuous insulation. Typically, this is done with thousands of screws or fasteners which pass through the continuous insulation, creating thermal bridges. Also, it creates thousands of holes through your air, water, and vapor barrier. There are non-combustibility requirements and fire rating requirements for load-bearing members and other components and exterior walls assemblies in the IBC. Chapter 6 deals with this. It states that types 1 and 2 construction are those types of construction in which the building elements listed in Table 601 are of non-combustible materials. There are some exceptions to the code, though. Type 3 construction is that type of construction in which exterior walls are of non-combustible materials. Type 4 construction is that type of construction in which, again, the exterior walls are of non-combustible materials. In Type 5 construction, the structural elements in the exterior and interior walls can be of any material permitted by the code. Chapter 7 deals with the fire rating requirements of load-bearing structural members within the exterior wall or on the outside of a building structure. They shall provide the highest fire ratings as determined in accordance with the following, which is Table 601 and Table 705.5. Cladding attachment systems are load-bearing structural members. They bear the gravity and wind loads imposed upon the cladding system. Cladding attachment systems that are made from or contain combustible materials such as plastics, fiberglass, and rigid insulation that bear loads can result in a life safety issue should the building catch on fire. Cladding materials falling off the building during a fire could endanger the lives of first responders as well as other people that may be in the area. This is Table 601. As you can see, for the primary structural frame, almost all types require a fire rating of the frame itself, and then bearing exterior walls require fire ratings in virtually all assemblies. For non-bearing walls and partitions, the code has Table 705.5, which lists the fire resistance rating requirements for exterior walls based on fire separation distance from adjacent buildings. Another code requirement is NFPA 285 testing. This is a multi-story burn test with a window in the lower floor. And basically it's a 30-minute burn and it tests for fire propagation. Failure criteria is flame spread and heat generated. Rain screen cladding panels falling off the test panel does not constitute a failure. Many of our competitors point out that test assemblies with their cladding attachment systems pass the NFPA 285 test, so their systems are code compliant. As I mentioned, NFPA 285 is only a 30-minute burn and therefore cannot be used to determine the fire ratings required by the IBC. The International Energy Conservation Code has a couple of requirements in there for exterior wall assemblies. They state the required U values for the assembly. They have both performance requirements and prescriptive requirements. It also defines continuous insulation. This is Table C402.1.4 from the 2021 International Energy Code. It lists the performance U factors for the various building enclosure assemblies. For metal framed exterior walls in climate zone 5, which is the climate zone that we are in, the U factor for the assembly needs to be 0.055 or less. The U factor is a measure of thermal transmission through the assembly. Many people in the industry do not understand this value well. The majority of people understand the R value well. The R value is the measure of resistance to thermal transfer through the building enclosure system. The inverse of the U factor is the R value. So again, looking at the 2021 International Energy Conservation Code, the U factor for metal framed exterior walls in climate zone 5 is U 0.055. As I stated, the U factor is the inverse of the R value, so you divide 1 by the U factor and you come up with an R value of R 18.18. This is Table 402.1.3. It lists the prescriptive requirements for insulation materials installed in the various building enclosure assemblies. For metal framed exterior walls in climate zone 5, it requires R13 insulation and R10 CI. The CI stands for continuous insulation. Here's a definition of continuous insulation that is in the International Energy Conservation Code. It says insulating material that is continuous across all structural members without thermal bridges other than fasteners and service openings. It is installed on the interior, exterior, or is integral to any opaque surface in the building envelope. The use of continuous Z-furring for attaching cladding systems to the building does not comply with the definition for continuous insulation. It creates a thermal bridge through the insulation, which substantially reduces the R value of the insulation to the point where both the performance and prescriptive requirements of the IECC are not met. Thermal bridging through the continuous insulation needs to be dealt with in order to comply with the performance requirements of the International Energy Code. This is Table C402.1.4.2. The IECC deals with thermal bridging of light gauge metal framing with insulation in this table. For an exterior wall assembly with 6-inch light gauge metal studs, spaced at 16 inches on center, with R19 insulation within it, the effective R value of this part of the assembly is only R7.03. The ICC does not have such a table for effective R value of continuous insulation on metal items such as continuous Z-furring pass through the insulation because this is not allowed per the definition of continuous insulation in the code. The effect of thermal bridging created by continuous Z-furring can be both visualized and calculated by using a computer simulation program called THERM, which can be downloaded for free from Lawrence Berkeley Laboratories. This assembly is comprised of 6-inch light gauge metal framing, 1/2-inch gypsum sheathing, 2-inch extruded polystyrene insulation, which is the R10 CI is prescriptively required in the IECC in Climate Zone 5, and an ACM panel veneer. Without the continuous Z-furring, the calculated R value of this assembly is R12.58. Factoring in the continuous Z-furring at 2 foot on center, the calculated R value of the assembly is reduced to R7.18, which is a reduction of about 43%. The R value of the extruded polystyrene is reduced from R10 to R5.7. This does not comply with the prescriptive requirements of the IECC. Filling in the light gauge metal framing stud cavity with R19 insulation would increase the R value of the assembly to only R12.73, which is the R5.7 of the continuous insulation with the Z-furring at 2 foot on center, and the R7.03 from the table which I previously showed you. This doesn't quite meet the R18.18 requirement of the code. The fastening of the continuous insulation layer can result in thousands of penetrations through the air, water, and vapor barrier. Here's a slide showing just that. On top of the thousands of holes through the air, water, and vapor barrier, these fasteners are expensive to buy and require a lot of labor to install, as the layout is critical to hit the studs with the fastener so that unfilled holes do not result in the air, water, and vapor barrier. It also represents thousands of thermal bridges through the continuous insulation. So here's what we came up with. The Stand Off MPV bracket. It's very low thermal bridging due to the diameter of the standoff which passes through the insulation and the spacing of it. It is adjustable. The top plate screws in and out. It doesn't burn because it's made of metal. It has few parts. It's easy to install. It's very cost effective. I think it's the most cost effective cladding attachment system in the industry based on the pricing feedback that we've gotten. We do have a seal at the fasteners that attach the base plate to the wall. As the fasteners, we require them to have a rubber gasket on them, and compressing the plate against the air, water, and vapor barrier turns the air, water, and vapor barrier into a gasket around the screw penetrations. It mechanically fastens the continuous insulation, so it doesn't require cutting and fitting the insulation around the brackets. We have not had any issues or complaints with the hundreds of thousands of brackets we have sold to date on projects. Here's a view of just the bracket. It's comprised of a base plate, the standoff, which is the round part, it's internally threaded, the insulation retainer, which in this picture it's black. We changed it to black because they weren't showing up on job site photos. And the top plate, which screws in and out of the standoff. And you'll notice what looks like a rivet here. And if you look at it from another view, we also have what looks like a rivet on the base plate. Here are the three components: the base plate with the standoff, it comes assembled. And then you have in a separate package the insulation retainer, and then the top plate, which screws in and out. The adjustability of the bracket is 1 inch, which is far greater than the industry tolerances for plane of the backup wall and the veneer. What I showed you were rivets in the top and bottom plate are actually called threaded studs, and they're called PEM studs. They're basically a threaded rivet that is impact driven into the top and bottom plates with a machine called a PEM serter. Once we had the design finalized, we took it to a structural engineer and we asked them to evaluate it and size up the components of the bracket. Here's a sketch the engineer developed for the cladding attachment system using the Stand Off MPV bracket. In his calculations, he calculated the gravity code to be 32 pounds, the gravity load to be 32 pounds, and the compression and tension loads to be 266 pounds. The compression and suction wind loads were based on 140 mile-an-hour wind exposure. These calculations are available on our website. We then took these calculated values and prototyped the bracket. We brought this to a testing agency, and they put it in their Instron machine, and they pushed on it, and they pulled on it, and they bent it. And the Instron machine gave out this output, which translates to a gravity load of 60 pounds and compression and tension of 550 pounds. So it was calculated for 32 pounds for bending. It came in at 60. Compression and tension were calculated at 266 pounds, and it came in at 550 pounds. So they came in about double the calculated values, which we were very happy with. What does this translate to in strength? Well, a 60-pound bending load will carry 11.25 pounds per square foot of veneer weight. We recommend limiting the cladding weight to 10 pounds per square foot. This will suffice for most cladding systems except thin masonry cladding such as granite, limestone, marble, and thin brick, which are around 16 pounds a square foot. For these cladding materials, the bracket can be spaced at 2 foot on center, which will now support a cladding system of up to 20 pounds. The compression and tension loads of the Stand Off MPV bracket can withstand wind loads that are equivalent to 292.56 miles per hour. The highest wind speed ever recorded in a hurricane in this country is 190 miles an hour, which was in Hurricane Allen, which hit Texas in 1980. There are several layouts that the Stand Off MPV bracket can be used in. This is the most typical layout where the brackets are spaced in 1 foot 4 by 4 foot, and hat furring used is the cladding attachment rail. If additional attachment surfaces are needed, flat stock metal in horizontal orientations can be added to the assembly. For long panel height claddings, the hat furring attachment rail can be attached in a horizontal orientation and the cladding system attached to that. If a 2 foot spacing height is required, the bracket can be spaced at 2 foot 8 by 2 foot. If more attachment surfaces are needed for attaching the cladding, flat stock metal can also be added to this layout. We analyzed the thermal performance of this assembly using 3D thermal imaging in a program called Heat3 version 9.01. RDH Building Science performed the simulation for us. This is the cover to the report. Here's the sketch that they used for the thermal modeling. And as you can see in the cutout section of the 3D thermal modeling, you can see the effects of heat transfer through the assembly. And it's only minimal where the standoffs pass through the insulation. RDH told us that they had to model the assembly with the Stand Off MPV brackets at various spacings as they felt that comparison to other cladding attachment systems was necessary for their analysis and those of their clients. None of our competitors' products can accommodate the 4 foot vertical spacing that our system can. This table shows the R value of the assembly is modeled. To achieve R 18.18 that's required for Climate Zone 5, you can use either 4-inch extruded polystyrene or 4-inch polyisocyanurate insulation in the assembly with their zinc and yellow chromate plated Stand-Off MPV brackets. For stainless steel, which doesn't conduct as much heat, you can use 3 inches of polyisocyanurate insulation, 4 inches of mineral wool, 4 inches of extruded polystyrene, or 4 inches of polyisocyanurate insulation. Other types and thicknesses of continuous insulation can be used in conjunction with the insulation in the stud cavity. However, we recommend that a hygrothermal analysis be performed on such assemblies to make sure it won't experience any moisture problems. The report also has a table for U factors. This report is available on our website also, and you can see that again, 4-inch XPS, extruded polystyrene, or 4-inch polyisocyanurate in conjunction with our rolled steel Stand-Off MPV brackets will comply with the code. If you change to stainless steel, which doesn't conduct heat as much, you can use 3 inches of polyisocyanurate insulation, 4 inches of mineral wool, 4 inches of extruded polystyrene, or 4 inches of polyisocyanurate insulation. We often get asked if our product passes NFPA 285. This is an assembly test, not a product or material test. With the Stand-Off MPV bracket being made from metal, we do not feel that it would add to the fire propagation or heat generated in such a test. We request an opinion letter from the person who actually wrote NFPA 285, Jeff Speitel, and received this letter for the low price of $5,000. Basically, he says that including the Stand-Off MPV bracket in NFPA 285 tested assembly would not affect the results of the test. This is the most typical installation of the Stand-Off MPV bracket. It uses hat furring as the attachment rail for the cladding system. We have seen the mini Z-furring used on a project, which we thought was odd, as the mini Z-furring has to be a much lower gauge of steel than the hat furring due to the eccentric load that it had to bear. We asked the contractor why they used it, and they told us that their structural engineer felt that using this was more comfortable using the Z-furring. Flat stock can also be used as the attachment rail. This will also have to be fabricated from a much lower gauge steel, as it is not as strong as hat furring made from the same gauge steel. This system was actually used in our first project, which is a hospital addition in Virginia, which has a zero lot line restriction, and they wanted to maximize the interior square footage of the building by making the exterior wall thinner. The Stand Off MPV bracket is offered at these standard sizes: 1.5 inch, 2 inch, 3 inch, 4 inch, and 6 inch. Custom sizes are available though. We have made brackets for 3.5 inches insulation, 5 inch insulation, and 8 inch continuous insulation. The finishes that we offer for our Stand Off MPV bracket are zinc and yellow chromate plating and stainless steel. Why did we use zinc and yellow chromate plating for our protection? Well, when the bracket couldn't be hot dip galvanized due to the threads, the components wouldn't thread together with the hot dip galvanizing plating. We didn't want to stamp the bracket components out of galvanized sheet due to the fact that the edges of the components would not be adequately protected, in our opinion. Ceramic coatings made the bracket more expensive than stainless steel. So we found zinc and yellow chromate plating offered the closest protection to hot dip galvanizing, which is pretty much the industry standard for components exposed to the elements in the exterior wall. Looking at the galvanizing process, there's hot dip galvanizing, which we found wouldn't work with our bracket. There's continuous sheet galvanizing. Again, we're concerned of cutting or stamping the components out of a continuous sheet. There's zinc painting, which would require the components all to be hung up and spray painted, and that was very labor intensive. Zinc spray metallizing, this was the same effect as the zinc plating. It would take a lot of labor to hang those up and spray them. There was mechanical plating, which we didn't felt that it offered as good protection as hot dip galvanizing. There's electroplate galvanizing, which again we didn't feel was as good as the hot dip galvanizing. And then the zinc plating, which we ended up using. As I mentioned, we chose the zinc plating as was the most cost-effective plating. The cost-effective plating was very close to hot dip galvanizing for protecting the steel used for the bracket. So corrosion resistance of the plating depends on the concentration of zinc in the coating and the thickness of the coating. Hot dip galvanizing has 98% zinc in the coating. ASTM A153 is the standard for hot dip galvanizing. It requires that it has 1.5 ounces of zinc coating per square foot of exposed metal, which translates to 2.2 mils of zinc coating of the component, or 1.1 mils of the zinc coating per side of the component. So zinc and yellow chromate, in comparison, has 98% zinc content per ASTM B633. And the class we chose was FE/ZN25, which requires that the plating be 98.98 mils thick. G90 galvanizing, which is used fairly often in exterior wall assembly components that are exposed to the weather, has 98% zinc content and is only required under ASTM A653 to have 0.81 mils thickness per side. ZM40 is another galvanizing system that was developed in another country. The developers marketed the idea that adding aluminum to the galvanizing solution made it superior to any other galvanizing process, and went to ASTM and got an ASTM standard, which is ASTM A1046, approved and published. The manufacturer of the cladding support system that uses plating offer their product specifications for architects, and it states that only ASTM A1046 can be used for the plating of their products, and no other ASTM standards can be used. So platings conforming to ASTM A153 and B633 and A653 have been used for decades and have performed very well. So this is the promotional piece for the ZAM 40. They applied for and received a registered trademark for the plating blend and called it ZAM. They call it ZAM 40. It's used for continuous sheet galvanizing, which we didn't like because the components of the cladding support system had to be either cut or stamped out of it. And we didn't really like it because they felt that adding the 6% of aluminum here made it this special coating that would outperform any other coatings or platings available on the market. This is a table from a publication called Zinc Coatings, a comparative analysis of process and performance characteristics offered by the American Galvanizers Association. And you can see by the chart that G90 galvanizing requires 0.81 mils of galvanizing per side, whereas G40 is 0.36 mils of galvanizing per side, which is similar to the ZM40, since that also requires only 0.36 mils of coating per side. In that publication is also a chart where it shows the time to first maintenance for the different coatings thicknesses based on the exposure. Time to first maintenance is defined as 5% rusting of the steel surface. So in a suburban climate, which is red, for 1 mil thick coating, time to first maintenance is 25 years. So taking a look at the various plating and coating systems there, hot dip galvanizing is 1.1 mils. So take that, multiply that by 25 years, you're going to get 27.5 years to time to first maintenance. For zinc and yellow chromate plating at 0.98 mils times 25 years, it's 24.5 years. So that was pretty close to the hot dip galvanizing, which is where we wanted to be. The G90 galvanizing is only 0.81 mils. That's 20.25 years, yet the edges of the components cut and stamped out of this continuous sheet galvanizing weren't protected in our opinion. The G40 galvanizing is 0.36 mils times 25 years is 9 years, and the ZM40 or ZAM40 galvanizing being only 91% zinc and 0.36 mils per side is only 8.36 years for time to first maintenance. The creators of the ZAM coating, when we questioned them about the cut or stamped edges, sent us this marketing piece. So they say when the substrate is cut or sheared or stamped or whatever, it will drag the galvanizing over the edge of that cut, and as it is exposed to the elements for time, it's going to flow over the cut edge, and there'll be a protective film there, and it's going to change from gray and then to black. We didn't believe this, and this picture confirms our conviction not to use this type of plating. This is a picture of flat stock that was stamped from G90 galvanized steel. The flat stock was 4 years old. The facade had to be removed due to numerous leaks into the building. But notice the rust that is showing up on the top edge of the steel. The galvanizing did not migrate to protect the edge of the steel. For our packaging, we chose 5-gallon pails with lids. The reason why is there's never enough empty 5-gallon buckets on a construction site, and we didn't want to have the workers have to take them down, the brackets down off the lifts every night, which they would have if we packaged them in cardboard. So we put them in a 5-gallon pail with lid. For the base plates, there's 100 to 200 pieces per pail. For the insulation retainer, we have 200 pieces per 2.5-gallon pail with the lid. And then the top plates are 200 pieces in a 5-gallon pail with the lid. Here's a project where Stand Off MPV brackets are used with 2-pound density closed cell spray foam for the continuous insulation. The base plates are installed, and then the spray foam was applied around them. Here's the project with the spray foam installed, and the top plates of the Stand Off MPV MPV bracket also installed, and the hat furring is partially installed here. Here's a picture of the same job with all the hat furring installed in a vertical orientation. And here's the siding, was fiber cement clapboard siding being installed on the project. Here's a picture of the project in progress. And here's a picture of the completed project. This project is a Midcoast School of Technology up in Maine. This is a project where the contractor used the mini Z furring. The cladding was full height metal panels with 4 inches of polyisocyanurate for the continuous insulation. Here's a view of the mini Z furring that was used on the project. Here's a view of the fluid applied air, water, and vapor barrier, the base plates of our Stand Off MPV brackets installed, and the continuous insulation installed. And down at the end, you can see some of the metal panel veneer that was installed. And here's an opposite view of that, showing the metal panel veneer. So this is the addition to the field house at Central Connecticut State University, where our Stand Off MPV brackets are used for the metal panel cladding system. The consultant on the job wanted self-adhering membrane over the base plates as a belt and suspenders to make sure the air, water, and vapor barrier didn't leak at the penetrations created by the screws used to attach the bracket base plates. Here's another view of the project where you can see the multitude of patches that had of self-adhering membrane that were installed on the project. Here's another picture of the attachment rail being in place. This one was a horizontal orientation, and you can see the Stand Off MPV bracket is also mechanically fastened the insulation, so you don't have a multitude of fasteners going through the insulation and through the air, water, and vapor barrier. So here's a picture of the metal panel veneers being installed on the project. Here's another picture pretty much showing all the components. You can see up top the base plates with the self-adhering membrane, the insulation, the top plates, the hat furring, attachment rail, and the metal panel veneer. And here's a close-up of the picture of the hat furring sitting on top of the Stand Off MPV bracket with the insulation retainer in place. This is the Henry James Middle School. The bracket spacing on this project is 1 foot 4 by 4 with hat furring installed in a vertical orientation. And that is because the metal panel veneer on this project is being installed on a horizontal orientation. So here's another view of the installation. This is the Morse High School project up in Maine. The spacing of the brackets are again 1 foot 4 by 4 foot. The hat furring was installed in a horizontal orientation, and the metal panel veneer was full height metal panels. The continuous insulation is 4-inch polyisocyanurate insulation. And here's a close-up view of the brackets, continuous insulation, and the hat furring. This is the addition of the Homer Babbage Library at the University of Connecticut. The veneer panels are ACM. They use flat stock fastened to the hat furring to give the contractor more surfaces to attach the ACM panels. You can see the ACM panels at the bottom of the picture. This picture shows the ACM panel veneer and the cladding support system. So if there's any questions, please feel free to submit them to me at len@exotech.biz. Any data you want or samples, we have all the test reports available on our website. I can send them to you also if you would like. We can send out samples and we can answer any questions you have about the system. So thank you for taking the time to view this presentation. I hope it was of some help to you.